This is part 13 in our series of lectures on section 2.5. In this lecture I'm going to do another example of the use of the principle of mathematical induction. I'm going to prove that every non-empty upper bounded subset of n has a biggest element. So here's the formal statement. Prove that every non-empty upper bounded subset of n has a biggest element. Of course, it's intuitively obvious that this statement is true, but a correct proof of it should involve some form of induction. We're going to formulate it in terms of a bunch of open sentences. So for each natural number, little n, we let P of n be the open sentence that every non-empty subset of n for which little n is an upper bound has the biggest element. So to say that n is an upper bound for that set is to say that n is greater than or equal to every element of that set. So what we'll do is we'll use the principle of mathematical induction to show that P of n is true for every natural number n. So before I show you my proof, let's just talk about it a little bit. The basis step would consist of you showing that P of 1 is true. So what does P of 1 say? P of 1 says that for any non-empty subset of n for which 1 is an upper bound, that set has a biggest element. Well, if 1 is an upper bound of a non-empty set, that means that a non-empty subset of the natural numbers, well then 1 is bigger than or equal to every element in that set, and the set is non-empty, so that set really has to be just simply the set singleton 1. It can't have anything else in it, since 1 is the smallest possible natural number. And therefore the biggest element is also 1. So that would show that P of 1 is true. Now when we're trying to deal with the inductive step, suppose we give ourselves some n and we make the assumption that P of n is true. How would we deduce that P of n plus 1 is true? Well, P of n plus 1 says that every non-empty subset of n for which n plus 1 is an upper bound has the biggest element. So if n plus 1 is an upper bound for this set, it might be true that actually n is already an upper bound for that set. If n is already an upper bound for that set, well then by the inductive hypothesis, that set must have a biggest element. But if n isn't already an upper bound for that set, but n plus 1 is, then that must mean that n plus 1 is in the set. And therefore n plus 1 would have been the biggest element. So that's the idea of the proof. I think we're now ready to do the proof formally, but since I've given you the main ideas, why don't you try to write down the proof yourself, and we'll compare our answers when you come back. Alright, well here's my proof. I'm proving that for every non-empty upper bounded subset of n has the biggest element. So for each n, let P of n be the open sentence that every non-empty subset of n having n as an upper bound has the biggest element. We will be done if we prove that P of n is true for all natural numbers n, and we're going to do it by principle of mathematical induction. Well, first we have the basis step. Let A be any non-empty subset of n for which 1 is an upper bound, then A must be the set singleton 1, and so A contains its biggest element, namely 1. Now for the inductive step, let n be a natural number, and suppose that P of n is true. We must deduce that P of n plus 1 is true, and so for that purpose, we give ourselves a set A, a non-empty subset of n, for which n plus 1 is an upper bound. Then we have to prove that that set has the biggest element. Well, if it's the case that n is also an upper bound for A, then by the inductive hypothesis, A would have a biggest element. But if it's not the case that n is an upper bound, then since n plus 1 is an upper bound, that must mean that n plus 1 lies in the set, and therefore n plus 1 would be the biggest element of A. So that proves that P of n plus 1 is true. And so it follows by principle of mathematical induction that P of n is true for all natural numbers n, and that completes the proof.